The revelations of the James Webb Telescope have attacked the case for the huge explosion. The James Webb Space Telescope has quite recently conveyed a by and large invigorating divulgence, genuinely sending shockwaves through the worldwide universe of material science. Through a single astonishing photo, it has crushed well-established conversations, leaving analysts essentially astounded. The time of speculation is finished, as Webb's latest catch is both outwardly flabbergasting and a game-changer that adds to shaping our convictions, influencing conversations among scientists. This photograph has unequivocally incited new methodologies. The impeccable picture caught by the James Webb Space Telescope is re-examining the way that we could decipher the universe. Join us as we investigate why it is certainly standing out enough to be noticed, and the way that James Webb's discoveries are shutting conversations in material science with a weighty picture. The essential trouble with cosmology is that scientists can't settle on how old the universe is or how rapidly it is developing. This unanswered peculiarity has confused researchers across ages, provoking different assessments to track down answers. Cosmology, the field of investigation zeroing in on understanding how the universe was made, how things are collected, and the way in which it has changed over time, has seen significant improvement throughout recent years. The current expansive cosmology model, the hypothesis of the enormous detonation, suggests that the universe has been growing from a hot and thick state for around 13.8 billion years. This development is measured through the Hubble constant, which indicates the speed at which the universe is expanding. However, estimations of the Hubble constant are not consistent. Estimates of the Hubble constant can be broadly arranged into two gatherings: nearby estimations and early universe estimations. Nearby estimations include the investigation of cosmic assortments of the universe. For example, Cepheid variable stars and type Ia cosmic explosion act as standard candles to check the Hubble constant. As a result of their brightness, astronomers can gauge how the universe's expansion influences the speeds of these objects to determine their distances and therefore calculate the Hubble constant. The subsequent gathering includes the assessment of the early universe. Scientists use observations of the cosmic microwave background, CMB, radiation, the glow of the huge explosion discovered during the 1960s. The CMB reflects the microwave radiation of the early universe when it was just 380,000 years old. By estimating the small temperature and polarization changes emitted by the CMB, space specialists can determine the age of the universe and its pace of improvement. But here lies the issue. The consequences of these two techniques don't match. The result viewed as through neighboring estimations confirms that the universe is expanding faster than what we measure based on CMB data. Due to these contrasts, analysts have been endeavoring to find the explanation for the conflicting outcomes. Further examination is being led to dive deeper into the universe's secrets. As things stand, the disparity in estimations suggests that there is either new science we have little understanding of or errors in one or the two techniques. On account of the James Webb Space Telescope, we can see into the dark universe more clearly than any other time in recent memory. The telescope can reveal the slightest and most far-off elements, planets, and worlds we could not have possibly thought conceivable to naturally see. Analysts expected that information from the JWST would help us in exactly figuring the Hubble constant. However, the underlying surge of information has surprisingly made matters more complicated. It has given new bits of knowledge that are not predictable with what we assumed we knew. Could this information lead to another theory and upset our comprehension of space? If so, we would need to review how we might interpret how the universe works. For example, we may find particles and forces that have never been noticed or could have to re-examine dark energy, a neglected component liable for the speeding up development of our universe. To date, the ways we ponder space have evolved as we keep on finding new things. For example, in 1965, when analysts found the astronomical microwave foundation radiation, it emphatically upheld the hypothesis of the enormous detonation. Previously, specialists believed that the universe was timeless, consistently growing at a uniform rate. However, new proof demonstrated that was false. Furthermore, when we found out towards the finish of the 1990s that the universe was constantly developing, we found dark energy and its effect on the universe's advancement. Thus, like perfect timing, when we research a novel, new thing, we question whether it squeezes into our existing system. If not, we grow new ways of understanding the universe better. Hence, the issue we face in cosmology today could lead to the revelation of huge responses about the universe. While the issue is challenging, it is also exciting as it moves us to foster further developed apparatuses to investigate space. This cosmological quandary also joins specialists from different countries, each anxious to get familiar with the universe. Overall, it shows that science is always changing and evolving as we look further into space. Alongside the Hubble pressure, there is likewise a test called the Paper strain, which relates to the spatial dissemination of matter in the universe. This can be utilized to make a chief picture of the universe and comprehend how it has advanced. Cosmologists allude to this peculiarity as lopsidedness, since there are areas of space with firmly gathered universes while different areas are meager. Scientists will utilize different methods to gauge this lopsidedness. One way is to concentrate on how light from far-off systems is bent by the serious gravity of huge items, for example, cosmic system groups. This curve, called gravitational lensing, gives an approach to analyze where matter is weak because it doesn't emanate light. Experts additionally use the vast microwave background, CMB, a shine from the very beginning of the huge explosion. This light has been going for near 13.8 billion years, conveying data from the early universe. Through CMB investigation, physicists can figure out how the universe became clumpy at its introduction to the world, which ought to match the observational lopsidedness of the universe on an enormous scale. However, these outcomes don't adjust. The CMB's clumpiness, given by the non-round gravity circulation model, recommends that the matter dispersion in the early universe was more homogeneous contrasted with what is tracked down utilizing gravitational lensing. This proposes that there might be something we are not taking into account in our clarification. This takes us back to the possibility of dark matter. What precisely is dark matter and how can it capability the fact of the matter is the issue stays unanswered. However, all trust isn't lost as the James Webb Space Telescope, JWST, is set to rethink the field of space science with its high goal and camera awareness. The telescope will look at the early times of the universe and investigate the primary cosmic systems and stars formed, making it conceivable to further develop estimations of cosmic expansion and matter dispersion. These key inquiries will require explicit perceptions and possibly new techniques. From a theoretical stance, to tackle whether the discoveries mean more noteworthy importance for dark energy, finding completely new physics, or acquiring a better understanding of dark matter's behavior, the outcomes will be extensive, addressing the universe's secrets. The discoveries made by the James Webb Space Telescope, JWST, are reshaping our understanding of the universe. While they challenge existing hypotheses, they also open new avenues for research and investigation. These findings highlight the dynamic and always evolving nature of scientific inquiry. With each new discovery, we gain a deeper and more nuanced understanding of the universe. That's what logical order, showing with each new discovery, we gain a deeper and more nuanced understanding of the universe. The latest endeavor, called Project Flamingo, is evidence of NASA's increasing enthusiasm for scientific exploration using one of the world's most powerful supercomputers located at Durham University in Britain. Project Flamingo is a remarkable achievement in computational development, requiring over 50 million hours of computer time and featuring 35 processors. The project highlights the scientific community's determination to explore the universe thoroughly, focusing entirely on dark matter, the mysterious substance that neither produces, absorbs, nor reflects light, but is inferred to exist due to its gravitational effect on visible matter. The approach of Project Flamingo is different from previous simulations, involving all possible forms of cosmic components, from galaxies with unusual gas content to stars and black holes at the universe's core. Through this systematic approach, the revolutionary change in the universe's description was generated from a key sketch. The motivation behind ambitious projects like Project Flamingo is clear: to make sense of astronomical phenomena where measurements appear imperfect and do not fit into the universe's plan. This difference in measurements indicates a significant gap in our current understanding of the universe's dynamics. Assuming these measurements were equivalent to musical genres, they would be like jazz and classical music, each having its approach while still related. Flamingo attempts to combine these different perspectives and refine our individual understanding of the universe. However, despite its sophistication, cosmic tension persists. This tension continues as humbling evidence that we have yet to resolve a crucial piece of the mystery surrounding us. The universe seems reluctant to share its secrets with us easily. Each new piece of data and simulation model added to our toolbox, like Flamingo, opens up an increasingly vast new universe with new challenges to address. It is a continuous journey where each answer leads to more questions, opening up an entirely new layer of inquiry. This demonstrates that the nature of our quest to unravel the universe's secrets is complex and ever-changing. Since Edwin Hubble made his outstanding discovery of the expanding universe in the mid-20th century, the speed of our understanding has been remarkably fast. Scientists are continually making specific discoveries about the universe's size, including the Big Bang theory, dark matter, and dark energy. They have focused on the cosmic microwave background, CMB, and meticulously recorded the positions and speeds of galaxies with increasing accuracy. Each of these accomplishments is like acquiring a new fundamental piece of the cosmic puzzle. This has led us to strive for a deeper understanding of the universe. Indeed, the universe is shrouded in mystery, and it may be risky to uncover its truths too soon. At every analytical step, researchers add refined theories, adjust models, and carefully craft inquiries. The theory of the Big Bang was once highly controversial but is now thought to be a fundamental piece of scientific knowledge. Similarly, dark matter is no longer a speculative idea but an apparent key component of a vast puzzle. The discovery of dark energy, an enigmatic force driving the accelerated expansion of the universe, was made in the late 20th century and is now one of the fundamental pieces of understanding the universe. Let us also consider technological advancements such as the Hubble Space Telescope, LIGO, and the James Webb Space Telescope. Each has opened new perspectives, allowing us to observe gravitational waves, distant stars, and the earliest epochs of the universe. Each innovative step takes us closer to understanding the mysteries of the universe. As we stand on the edge of new discoveries, perhaps we are uncovering answers and engaging in a broader and more nuanced appreciation of the universe's operations. It is an exhilarating and ever-evolving journey filled with wonder and revelation. Surely, we should dive further into every aspect of the discoveries made by the James Webb Space Telescope, JWST, and how they challenge our current understanding of the universe, particularly the theory of the primordial cosmic explosion, the Big Bang theory, and Hubble constant. There are two primary methods to measure the Hubble constant. 1. Local measurements using Cepheid variable stars and type Ia cosmic explosions as standard candles to measure distances within our galaxy and nearby galaxies. Tension in local measurements suggests a faster growth rate than measurements obtained from the early universe. 2. Early universe measurements using the cosmic microwave background, CMB, which is the afterglow of the Big Bang. Measurements of the CMB, like those from the Planck satellite, offer a different value for the Hubble constant, generally indicating a slower expansion rate. The discrepancy between these two sets of measurements is known as the Hubble tension. The role of the James Webb Space Telescope, JWST, was designed to explore the universe in extraordinary detail, offering insights into the early universe, galaxy formation, and more. Its discoveries have raised new questions and provided data that sometimes conflicts with our existing models. Key discoveries and their implications include early universes. JWST has identified galaxies that are much older and more developed than expected, suggesting that these galaxies formed sooner after the Big Bang than current models predict. Cosmic structures. JWST observations reveal a more complex structure of the universe's early stages than previously thought. These include complex formations of galaxies and intergalactic gas, suggesting that the process of structure formation in the universe may differ from our current theoretical models. Dark matter and dark energy. JWST's detailed observations help map dark matter distributions by analyzing gravitational lensing effects. Understanding the distribution and behavior of galaxies and dark matter refines models of dark energy, the mysterious force driving the accelerated expansion of the universe. The inconsistencies and new findings by JWST could indicate new physics. There may be unknown particles or forces influencing the universe's growth and structure formation. Revised models. Current cosmological models may require adjustments to accommodate new data. This includes reevaluating aspects of the Big Bang theory and the roles of dark matter and dark energy. Revised understanding of cosmic legends. The early universe may have undergone more rapid and complex development stages than previously recognized. The processes leading to galaxy formation may be more efficient or divergent in nature. Project Flamingo, an ambitious simulation project, aims to reconcile these disparities by simulating the universe's development with high precision using one of the world's most powerful supercomputers. The project includes detailed simulations, comprehensive modeling of galaxies, stars, black holes, and intergalactic gas, simulating various cosmic components and their interactions over time. By systematically testing hypotheses against observed data, Project Flamingo aims to provide more accurate predictions that align with observations from JWST and other instruments. The discoveries made by the James Webb Space Telescope, JWST, are reshaping our understanding of the universe. While they challenge existing hypotheses, they also open new avenues for research and investigation. These findings highlight the dynamic and always evolving nature of scientific inquiry. With each new discovery, we gain a deeper and more nuanced understanding of the universe.